Exercise 12b. Let's have a look at 1. The area A of a circle of radius r is given by the formula A equals pi r squared. A, find dA dr. Well, we differentiate this. We bring the 2 to the front, and it's 2 times pi r. This becomes 2 minus 1, which is 1, and we end up with 2 pi r. B, find the rate of change of the area with respect to the radius when r equals 2. Okay, we can see this rate of change, so we're going to use this equation here, and we've got 2 pi r when r equals 2. That's 2 times pi times 2. 2 times pi times 2 is 4 pi. Question 2, the profit, US dollars, P, made from selling cupcake C is modeled by this function. Find dP dC, well, we can do that. That 2 comes down to the front, so we've got the 2. I've put it here because of the minus sign, but it's 2 times that number, the coefficient of this C squared term, plus 5.6 times, effectively that's a 1 there, so the 1 comes down, so it's 5.6 times 1. Now that C becomes 1 minus 1. Okay, you don't normally write this line, I'm just writing it to make for clarity here, and that derivative of a constant is 0. So we resolve this, and it's 2 times this number, which is minus 0.112, and this one becomes 2 minus 1, which is C, which is to the 1, right? You don't write the 1, and this is C to the 0, so that's 1, so it's just 5.6 times 1, which is that number there. B, find the rate of change of the profit with respect to the number of cupcakes when C equals 20. We just put 20 in here for C. When you see rate of change, we're going to use this one here, the derivative. So we put the 20 in, and we get 3.36. That's a positive number, so the rate of change, the profit's increasing with respect to the number of cupcakes. And when we put the 60 in, the profit is decreasing with respect to the number of cupcakes. Comment on your answers for part B, and this is from the back of the book. At the larger number of sales, selling more cupcakes will decrease profit. Profit's decreasing. The rate of change is decreasing there, whilst it will increase profit at the lower value. So at 20, it's a positive rate of change, and that's from the back of the book. Okay, let's have a look at number 3. The distance of a bungee jumper below his starting point can be modelled by this function, and that t is greater than or equal to 0 and less than or equal to 2, where t is the time in seconds. A, find the derivative of this function. And we do that, we bring the 2 down there, and it becomes 2 times 80 is going to be 160t. That becomes 2 minus 1, which is 1. This is minus 160 because that's t1. Bring down the 1, that's 1 times minus 160, and that's 160 times 1, and then t becomes 1 minus 1 power, which is equal to t to 0, which is equal to 1. It's a bit complicated the way I've explained that, but if you know how to take the derivative, it's just 2 times 80 times t, and then minus 160, and that's what we have here. B, state the quantity represented by the derivative. Well, the derivative is the change in the rate of change of d with respect to t. Now, I've used d for distance, and t is time. Well, that's velocity because it's a change of distance over time. So that means the derivative here is the velocity of the bungee jumper. C, find the derivative at 0.5 and also at 1.5 and comment on the values obtained. So at 0.5 we get minus 80. Okay, make sure we're using the derivative equation, which is this one here. And then at 1.5 we get 80. So that's minus 80. This is 80, traveling at the same speed but in opposite directions. D, find the function at 2, right? Be careful here. This is asking us the derivative at 0.5, x 0.5. This is asking us about the function. So we go back to the original function here, that one. And we substitute 2 in, we put 2 in there, and we get 0. Now, I think the back of the book had a little bit messed up, so I took that out. But the argument is okay here. It says, comment on the validity of the model. The bungee jumper passes through the start point at the same speed that he left at, which is 0. This is unrealistic, as some energy will be lost, for example, in overcoming air resistance. Okay. Question 4, points A and B lie on the curve of this function, and the gradient of the curve at A and B is 3. Find the coordinates of the points A and B. Well, we take the derivative of this, and that gives us an equation that would tell us the instantaneous rate of change, or the slope at a particular point of x. So we've done that. That's that. 3 down to the front. That's 3 minus 1 is 2. 2 to the front, 2 minus 1 is 1. And that one is 1. So 1 times 2 is 2. X to 1 minus 1 is x to the power of 0, which is 1. So that's our derivative of this function. Now they told us that at A and B the gradient is 3. At A and B the gradient is 3. Therefore, if this function here now tells us the gradient, and we know the gradient's 3, we just have to find the value of x. So we put 3 here, that's the gradient, that's that. This equals this, okay? We solve for x, we're going to factorize this, and it factorizes there, and we get x equals 1 on 3 and minus 1. Okay, so just recapping on that, what this means is at x equals 1 on 3 and x equals minus 1, the gradient is 3, because we use this, and that tells us the gradient at points, values of x. So we wanted to know the value of x where the gradient was 3. And we've found 2 values of x where the gradient is 3, and they told us that's at point A and point B. The value of the function at x equals 1 on 3. Now we take the 1 on 3 and we put it back into the original function because we want to find the function value, or effectively the y value. Okay, so you put 1 on 3 in here. I've put 1 on 3 for x, 1 on 3 for x, and 1 on 3 for x. And we get 22 on 27. So that means that at x equals 1 on 3, the function value is 22 on 27, so we can write that as a coordinate point. That's the x value, that's the y value, or the function value, 1 on 3 and 22 on 27. Now the value of the function at x equals minus 1, that was our other value here. We just put minus 1 back in the original function. That's minus 1 to the third plus minus 1 squared plus 2 times minus 1. That's that. Comes up to minus 2. So at x equals minus 1, the function value is minus 2. That's the coordinate point, and that is the same as they've got here in the back of the book. Question 5, the outline of a building can be modelled by the function, this function here, where h is the height of the building and x the horizontal distance from the start of the building. So that's the front of the building here, the start of the building, and that models the shape of the building to here. An observer stands at point A. We don't know the point A, but we know it. We just labelled it A, but we don't know where that is. The angle of elevation from his position to the highest point he can see on the building is 45. So if you draw, that's his line of sight. It goes straight up there and it just touches the curve here. I'm going to call that B, that point B. We know the angle is 45 degrees. So I've drawn this little diagram here. Calculate the height above the ground of the highest point he can see on the building. So we want to find this value here, which is effectively that value there, right? So there we go. And we're going to do it in 2 steps. We're going to find x. Once we find x, we can then put that back into the original equation and we can find the height there. Okay, so we're going to do that here. Now, the first thing we need to realize is they told us that the line of sight is at 45 degrees. Well, if the line of sight is at 45 degrees, that means the rise is 1 and the run is 1, rise over run, or the tan of 45 is 1, right? Tan of 45 is 1, we know that. So that means that the slope is 1. We know the slope of this line is 1. Where it touches at B, because it's exactly the same point, it just kisses it there, then that means the slope of the function, the gradient of the function at that point, is also 1. So what we need to do is find the equation that's going to tell us the rate of change of this function here, right? It's going to give us the gradient at any point of x. We're interested in this point here. So at point B, the line and the function kiss at the point xy. We'll just call that xy. That's what we're looking for. At this point, the line and the function have the same gradient. Okay, so if the line has a gradient at that point of 1, because we know the gradient of the line is 1, the gradient of the function is also 1 at that point, we can find the derivative and equate it to 1 because we know the slope is 1. So the original function is this one. The derivative of this is this. All right, it's 2. And it's bring down the 2 and you've got minus 0.2x to the power of 1. Remember, this function represents the gradient at any point along the function. It represents the gradient. At point B on the line and the function, the gradient is 1. So we know that the gradient of the line is 1 at that point B, and the gradient of the function is also 1. So all we need to do is equate this equation here, the derivative, to 1, because we know the slope at that point is 1. We just need to find what the value of x is. So 1 equals 2 minus 0.2x, and we resolve that to x equals 5. Now find h at x equals 5. So we found the point x equals 5. We've got to find out what the height is. The way we do that is we put the x equals 5 back into the original equation of the function. We put 5 in there, 5 and 5. That's back into this one. And we get the answer is 7.5. Now 7.5, it doesn't say meters. So I've just put units. In the back of the book, they say it's meters. So basically, the x value is 5 and the function value, which is the height here, is 7.5. But this doesn't represent this very well because on here, that's actually not 5, is it? because there is 10. 1, 2, 3, 4, 5. That's 10. So 5 would be here. So it just doesn't kind of match, and 7.5. But that is the coordinates there of B, which is 5 and 7.5. So X is 5 and H is 7.5.